Hello everyone, we're Group 3 and our final machine learning project is on NBA player performance on salary. So a quick look at our table of content. In the first section, we have the introduction of data, where we'll be covering the background of NBA and providing a quick data summary. In our second section, we will be talking about preliminary analysis and inference model, where we'll take a look at our inference model and our interaction and polynomial formulas. And in our third section, we'll be covering prediction model, where we'll talk about our feature selection using LLS, backward, forward subset, lasso, and ridge models. And last but not least, in our fourth section, we'll be providing our comparison and conclusion on the models and be stating our inference and which is our best model in the end. So a quick look into our introduction. Our introduction surrounds our analysis and research on the National Basketball Association, which is also known as NBA, and it is a collection of 30 professional basketball teams in the United States and Canada. And NBA is currently the third largest professional sports league in North America, and it has approximately $264 million in revenue in 2021. And with this size and vast revenue in the association, there are many scholars and fans who take great interest in the salaries of the NBA players. And there have been a lot of research in determining the factors that greatly affected players' salaries. And there are simply so many statistical variables. And we dedicate this project into finding what are the most significant variables that may contribute to an NBA player's salary using the NBA.full data set we were given. So a quick look into our data summary. So our data source is from the website Basketball Reference, and we are using a class-provided data called NBA.full.rdata, and it is a time series data set. So the data set covers the full statistics of NBA players from 2001 to 2019. And the data structure consists of 7,271 rows and 39 columns. And there are 39 variables in total and 7,271 observations. So first, we're going to go over our dependent variable and our independent variables. So our dependent variable is the inflation adjusted salary of individual player. And for our independent variables, there are a lot of statistical variables. Going further to explain our independent variables in detail, for the field goal percentage is the number of shots made divided by total number of shots attempted. And for the field goal 3 points percentage is the number of 3-point shots made divided by the total 3-point shots attempted. And for the free throw percentage are the foul shots made behind the free throw line divided by all the foul shots attempted. And for the effective field goal percentage, it is similar to the field goal percentage, except in this effective field goal percentage, 3-point shots are worth more than 2-point shots. As you can see, we also listed the formula of calculating it, and the data set has provided this data already to us. And this is just to explain how the effective field goal percentage works. And then there's turnover, is when a team loses possession of the ball to the opponent before getting a shot at the basket. And then there's the variable of the minutes played, which is the minutes played by players in each game. And then there's the offensive rebound percentage, which is offensive rebounds made divided by the total offensive rebounds attempted. And then there's defensive rebound percentage, which is the defensive rebounds made divided by the total defensive rebounds attempted. And then we're going to go and take a look at our data summary. And below, we provided a table of all of our numerical data and statistics. For our data summary, we found two distributions that are really interesting and stood out to us. So we provided the graphs and attached them on the slide. And as you can see on the left is a box plot on the adjusted salary and position, where you can see comparing the 5 positions and their relative adjusted salaries. The center actually has a relatively just slightly higher mean salary compared to the rest of the positions. And also the power forward is a little bit higher than the rest. And for the graph on the right is a scatter plot of adjusted salary and age. And this is also a very interesting distribution that stood out to us because we can kind of tell there's a trend where as we approach the age of 30, and also the gap between 30 to 35, the adjusted salaries is actually getting very high, and you can see the distribution has become more cohesive. During that part on the scatter plot, there are more data points. The data points are closer and relatively higher compared to the other age range, which is also kind of true compared to the consensus, which is that NBA players usually reach their peak performance at the age between 30 and 35.
So now I'll go over the preliminary analysis. Originally, we have 7,271 observations from the raw data set, and among those, 2,427 observations are outliers, and after deleting those, we are left with 4,844 observations. So with those data, we ran the regression and found out that there are 15 residual outliers. So after deleting those outliers, we are left with 2,442 observations. And those will be the observations that we continue using for this entirety of the project. We realized we had a very significant issue from the beginning. The issue was that because our main variable of interest is NBA player salary, so that was very much affected by factors such as inflation. So it was very essential for us to convert the salary of those players to 2018 dollars so that we will be looking at salary in the same year. And here I listed the future value and present value equation. So future value equals the present value times 1 plus the discount rate to the power of years. And for example, if we want to calculate the future value of 2010, so we would use year 2018 minus year 2010, that gives us 8 years. And for the discount rate, we went on the Federal Reserve website and downloaded discount rates from the year 2000 to the year 2018, and we averaged all of these discount rates. And that is the discount rate that we used in the above equation. So our final product is the adjusted annual salary from the calculation from the above equation. And then we take the log of the adjusted annual salary, and that will be the dependent variable in our model. We also included a correlation table in our preliminary analysis. And as we can see that there are very high correlations among some of the variables. For example, the correlation between ft.pct and fg3.pct is 0.33%, and the correlation between defensive rebound percentage and the free throw percentage is 0.35%, and those will be further discussed in our inference model and also the prediction model as well. So with all the independent variables we had and the adjusted salary log, we ran a multiple variable linear regression. And on the right and on the left, the graphs were, we plotted the residual value graphs. And as we can see from the graph on the right, the zero conditional mean assumption was very clearly violated since a lot of those blue lines are curved, especially for the age variable on the bottom. The blue line is very clearly curved down. So that means that the age variable probably has nonlinear impact on the model, and that will be further discussed later. And for the graph on the left, it is a residual graph plotted against the fitted values. And the curved line also suggests that nonlinear terms needs to be added to the model. So we can draw some conclusions from the preliminary analysis that we had. So first of all, the zero conditional mean assumption was clearly violated, which means that we need to add more nonlinear terms. And second of all, there are some very high correlations that exist among our independent variables. So we will need to create interactions among those variables. And then thirdly, for the from the previous fitted value graphs, we also thought about the possibility of outliers, but because we deleted those outliers in the beginning of our analysis, so we kind of just eliminated the possibility of that. And from these three conclusions, they provide reasons and evidence for our inference and prediction models, which will be coming up next.
After proposing the initial regression model, we plotted residuals for all the independent variables. Based on our observation, there's only one independent variable, h, violates against the zero conditional mean assumption. Here we can see that the blue line is curved rather than being straight. So we decided to add in quadratic term for h as a new independent variable into our model. Then we summarized the regression result and performed a robust error correction on the model. The results are above, and as we can see, most of the variables are significant, and all significant variables remain significant after robust error correction. We can see the robust standard error changes only by 0.0022. We interpret the results for all the significant independent variables, and here's what we get. A player's salary gets positively affected by the minutes a player played per game. 1 more minute played corresponds to 4% increase in salary. 1% higher in turnover rate corresponds to a 32% increase in salary. 1% increase in offensive rebound corresponds to 1.26% decrease in salary. A player's salary is also negatively affected by the position he plays. From the result, the center gets paid the most, while the point guard gets paid the lowest. Finally, age has a negative effect on a player's salary. However, since the relation between age and salary is nonlinear, the negative effect gets larger as a player gets older.
And for our second inference model, which is the interactive polynomial model, so here I'll be going through the process of how we came up with the interaction model. So from the previous preliminary analysis, we created the correlation table among all the independent variables. And here we take every single variable pair and write down the ones that have very high correlations with each other. So those are listed on the right of the slide. And we came up with this equation on the bottom where it's all saved to r.interactive. So the key inference questions that we want to answer is whether the correlation between those pairs will affect our regression result. And those pairs specifically were free throw percentage and field goal 3 points percentage, field goal percentage and effective field goal percentage, offensive rebound percentage and field goal percentage, defensive rebound percentage and field goal percentage, minutes played and free throw percentage, offensive rebound percentage and free throw percentage, minutes played and the turnover rate, effective field goal percentage and minutes played. And with the equation from the previous slide, we were able to run multiple linear regression with those interaction terms that we created. So among all of these interaction terms, in total, there were 10 of them. We found out that field goal percentage and offensive rebound percentage and field goal percentage and defensive rebound percentage are significant. And we compare the R squared without the interaction from previously to the R squared with the interaction model that we are doing right now. So the R squared from previously was 0.5439, and the new R squared is 0.5466. So we can clearly see that the R squared has increased with these interaction terms.
Utilizing a predictive model, we can evaluate on how to best predict individual salaries of NBA players by finding the most optimized model, which helps to assess which key variables contribute influence to player salaries. The main dataset MBA was first split into two datasets, train and test datasets, by randomly sampling 80% of the data into a train dataset and the remaining 20% of the data into a test dataset. There are 3,875 samples in the training data and 959 samples in the testing data, and each have 11 original features. The models were trained on the train dataset and then evaluated on the test dataset. The 5 candidate models include the following: the OLS model, best backward subset model, best forward subset model, ridge model, and lasso model. In selecting the most accurate model, the feature selection prediction model compares the 5 candidate models based on the performance measure of mean squared error, MSE. In the OLS model, the model includes all pairwise interactions and main features. In the backward subset model, the model begins with a full model, a model containing all predictor variables, and then removes the least significant variables one after another. The best backward subset model is chosen based on the maximum adjusted R-squared. In the forward subset model, the model begins with a null model, a model with no predictor variables, and then adds the most significant variables one after another. Similar to the best backward subset model, the best forward subset model is also chosen based on the maximum adjusted R-squared. Ridge and lasso are shrinkage models, shrinking variable coefficients towards zero. Ridge and lasso are both used to reduce model complexity and prevent overfitting from a simple linear regression. The best ridge model was selected using 10-fold cross-validation to find the best lambda, minimizing the error as shown in the following figure. Similarly, the best lasso model was also selected using 10-fold cross-validation to find the best lambda, minimizing the error as shown in this figure. After creating the 5 candidate models based on the trained dataset, each model was applied to the test dataset to evaluate predictability. The model shows the MSE values for all 5 candidate models, where the best backward subset is the best pairwise interaction model, as it has the lowest MSE on the testing data. The model most closely fits the test dataset. Model 4 was the polynomial predictive model. The model consists of 5 candidate models with linear and polynomial terms, from a model with all linear terms to a model with a linear term and variables up to the power of 5. Through 10-fold cross-validation and running a loop cycle through the polynomials to return the MSE of each model, the quantic polynomial model returned the lowest MSE value. This means that the quantic polynomial model has the best prediction accuracy.
From all the analysis above, we can draw some important conclusions and comparisons. So I would like to say that the 2 main areas of interest from this project is to determine which interaction variables are the most significant to the models that produce the lowest error. And the second one is whether or not adding polynomial terms to a variable can lower and give us better result. So the inference model, polynomial model, and our model 4, the prediction polynomial, basically solve the same question. And similarly, the model 2, which is the inference interaction model, and the model 3, prediction feature selection, solve similar questions. So I'll be comparing model 1 to model 4 and model 2 to model 3. So if we compare model 1, the inference polynomial model, to the model 4, prediction polynomial model, for model 1, our R-square was 0.5499, and the new R-square is 0.5748. So the R-squared has increased significantly with the prediction polynomial, which means that after adding the age to the power of 5, that has accurately increased the effectiveness of our prediction of our polynomial model. And then comparing model 2 to model 3, the inference interaction to the prediction feature selection, the old R-square was 0.5466, and the new R-square is 0.5696. And similar to the last one, the prediction model also performed better than the inference model. And in the feature selection, it turned out that the backward selection was the best model that produced the lower MSE. And from the inference interaction, we only created 8 interactions. However, in the prediction feature selection, the machine created 85 variables.